Welcome to meeting 103, guys. We're going to start off with reverse engineering tonight, and we're going to continue doing that for the majority of this semester and probably the majority of the spring semester too. It's a lot of fun, but a ton of content. So we're going to teach you the basics tonight, and also one big announcement that I already made, elections are coming up, so feel free to apply the forms in general. And if you guys aren't in a committee, join a committee. Looks like we've done most of our stuff for this semester, but NSA Codebreaker Challenge is currently going on. It ends in February, I believe.
It's like January.
January? Okay.
9 days or something.
Yeah, we've got plenty of time, but you should definitely do it and get us points because we're currently number 5. That's our position, and we can absolutely get to number 4. We're pretty close.
If we stay in 5th, we get to get put in the presentation next year.
That's true. You guys, I don't think he showed us that part of the presentation in here. Right?
No,
that was in Franco's class. But Jason Armstrong from the NSA last week was showing in his presentation that all the people that were in the top 5 last year, and we could absolutely be in that. But anyway, Rockwell Automation visit on the 30th and club elections on the 6th. Oh, here's a little bit more about Rockwell Automation. I haven't read through this actually. Bring resumes. And Mike has organized that, so reach out to him if you have any big questions.
Alright, so because it's midterms week, I only have one thing to talk about. VPN Breach. You guys have probably heard about this. Has everyone heard about this so far? Okay, cool. So you probably know what's going on. So basically, NordVPN had a breach that everyone made it sound like it was a really, really big deal. Really, nothing got leaked. It was just like, hey, someone got access to a server. But basically, the company who NordVPN works with to rent out servers had a insecure remote management system, and they didn't tell NordVPN about that. So when it got breached, the server provider just deleted the account and then just didn't tell NordVPN about it. It was very shady. As soon as NordVPN found out about it, they said no and canceled their contract and shredded all the servers. It happened back in March of 2018, so it was a really long time ago, but they just now released a blog post about it. The reason they waited so long is because they didn't know if this same configuration was on other servers, because they have 3,000 of them. But yeah, basically they had a expired public key, or not public key, it was basically a key pair. But the attacker could have used that key pair to spin up their own servers, and then if a user tried to authenticate with NordVPN, I think what would happen was it would just check that key and it would say, hey, this is expired, but if the user just clicked go ahead, they would actually be connecting to the attacker server.
It was a TLS key, right?
Yeah. Okay. So in NordVPN's posts, they said it would be very difficult to actually utilize the key in any way for probably that reason, that you actually need user input to do anything with it on the client side. Like I said, it was one of 3,000 servers, so one in Finland or something, so it's very small, and that's really about it. They didn't say much more, but they made it a big deal, but nothing really got out. So, does anybody have any questions about that? Any comments? Does anybody use NordVPN? No? Okay, cool. They're mining your data, so it's good.
Whee!
All right, so we're going to go over the basics for reverse engineering tonight. Reverse engineering is abbreviated RE, so sometimes it's called reing, but that's not correct. So here's the agenda for tonight. As always, we'll talk about what we did in last week's. We'll go over the concepts of what we're about to do and then the tools. and then we'll just dive right into a practice problem from Mattel that they had at a CTF, is that 2017, that we have used a lot to train people on reverse engineering. It's a very introductory level problem. So we're only going to go into the binary in the code. We're not going to go into any kind of stack exploitation or anything. We're just going to do finding out what the program is trying to do and what inputs it's looking for in order to give us a secret that it has. So if you weren't here last week, shame on you. We had Jason Armstrong come from the NSA, and he gave just an awesome presentation on the history of encryption, and he even gave us he didn't give us. He brought an Enigma machine, put it right there, and we all got to play with it. It was an original Enigma machine from World War II. It was actually carried by German soldiers. I think the NSA has like 2 of them that they tour with.
I think there's more than 2, but he primarily uses like 2 different kinds.
I think that was the one from the Cryptologic Museum. I think they have 2.
They both are. Basically, the 2 was there's a wooden one and a metal one.
Yeah, he brought the metal one.
Yeah.
So, yeah, it's a very interesting thing that he had in the Pelican case, and he said he just like threw it on like luggage overheads because that's how you move it around. It weighed like 50 pounds.
Basically stays attached to him at all times.
Yeah, they're not cheap. They're quite expensive collector's items.
I think he said somewhere up to $80,000.
Yeah, so that was pretty cool. You don't get to see that every day. So this is the NSA's Earth Day mascot. His name is Dunk, and he came out in a Freedom of Information Act request. He's something to look at. I felt like throwing it in. His voice also does not match him. Yeah. All right. So what is reverse engineering? Reverse engineering is taking a piece of software, specifically software reverse engineering, is taking a piece of software and putting it through tools to see how it behaves and if we can manipulate it in any way. This is typically done with a combination of debuggers, which most IDEs have debuggers in them when you're building software. Most debuggers can be used to profile built outputs for your software projects without actually having the source code in it. It's just going to be a lot harder because you won't see what your source code lines are executing. Disassemblers are also useful. They take machine code, and sometimes they can do byte code for languages like Java, and they try to turn them back into at least some kind of intermediate expression. So that won't be back into like C code. It'll take you from a binary and bring you back to like whatever your machine code was, so you'll be able to read it in assembly pretty nicely. And then decompilers are more advanced than that, but they become a lot more common, especially this year with the release of Ghidra for free. So last year, this time, a good decompiler would have cost you like $1,000 license every year. Now Ghidra's free, and we can put pretty much any binary in it and get it right back to C code. That's pretty powerful to the point where like pretty much every CTF we've gone to this year has just drastically changed after March, because that's when Ghidra came out. So that'll take a program and try to turn it back into like somewhat readable source code for you to play with. I can build a Ghidra and show you guys what that looks like with the NSA challenge, where you have an APK, which is an Android application, which is written in Java, but then it does decompile back for you a lot. And then static analysis is everything that we'll do without running the program. And then dynamic analysis is actually inspecting the program as it runs. So we can open, say, GDB, which is the GNU debugger, which is meant for native executables on specifically Linux systems. And we can like go through a program and see what it has on its stack and see what inputs it's kind of using for its functions. And then we can see if it's calling a lot of crypto. We can really see what the program is doing, but we can usually do very similar stuff through static analysis, although it might not be as quick. Usually if you're analyzing anything, you'll need a combination of both. And then why reverse engineer things? You can figure out how they work, change how they work by extending them or just giving them certain inputs. If you find a software-defined password, so if you have something that's like a regex that checks for a certain kind of input, which might be used for like a software license key, you can determine what the regex they're using and give them a correct key. And you can also find vulnerabilities and then exploit them. That happens a lot with CTFs. So the reason you would use reverse engineering is to make exploits, to hack video games, win CTFs, things like that. Codebreaker does involve a little bit of reverse engineering this year, but not super in depth, at least not up to part 4.
Task 5 is a lot.
It gets harder. but it's also an Android, which is really cool. So if you ever see people running around with like aimbots in video games, at some point someone reverse engineered a part of that game so they could reach into the world state, change the pointer to be over the other character, and then shoot. That's a very, very common one. That's aimbots. You can do all kinds of things once you get, the ability to manipulate a world state in a game or just any piece of software. You can do a lot. I actually have this tab open. So I found this today. This is a analysis of the BattleEye anti-cheat engine. This is a bit more dense than what we'll talk about here, but BattleEye is the anti-cheat engine that is used by Fortnite and a couple other games. I think Rainbow Six Siege uses it. So this is actually something that would be looking for you to be hacking a video game, and someone went through and they reverse engineered it, and then they found hacks for that. So it gets really meta really quickly. Yeah, this is a little bit more in depth than we'll go, but it's still really cool that people can just look at like bytes on a network and find this kind of information on it. Let's go back to this. So reverse engineering tools, typically when you have a binary, it falls into one of two categories, which is native or interpreted / semi-compiled. The native stuff includes ELF's portable executables and Macho, which is the Mac OS X version of a native binary. They do weird stuff to it. So PE is Microsoft portable executable. If you have an EXE or a DLL, it is in that format. Typically, they have two main sections to them. One is called the DOS stub, which is just a print statement for this program cannot be run in DOS executable mode. So that's quite the compatibility layer they have for their older systems. And ELF is extensible linker format. They renamed it. So that's what a.out, if you do GCC on Linux, will put out. What are you guys laughing about?
The tool.
Oh yeah. So these are our tools. We got Chris there. You said you wanted to be in the slides.
I didn't want to be in the slides, not like this.
Yeah. So an example on the not compiled but interpreted side of things, Java and Android are really Android is in Java, but an extension of it. Those will be compiled down to bytecode, which is an intermediate language format, which doesn't mean it's going to run on your native hardware. The Java interpreter, engine, machine, virtual machine, when it sees that code, it compiles it natively as it runs it. So that's a little bit of a different process, but through Ghidra, it's pretty much the exact same because Ghidra has a lot of higher level functionality in it. It'll turn it right back into C-like code for us. So we can skip a lot of stuff very quickly. So if you've not seen Ghidra yet, it is a NSA reverse engineering tool that became declassified in sometime last year.
March.
And then they released it in March. So you can get it from their website at ghidrasre.org. ghidrasre.org. So if you don't have it already, just go ahead and download it. This does require a Java SDK version, which I believe
11
is
or higher.
Yeah, 11 or higher, and it's under their installation guide. Does anyone not have this set up and need some time to get it? Okay, cool, because I've got some more slides I can talk through. But this is at ghidra-sre.org, or if you just type in Ghidra or NSA Ghidra into Google, it should come right up. So that's what we're going to be using because it's very easy and also free, which is what we want. So let's just talk about the compilation process of a native executable for a second. So when you take your source code and you feed it into your compiler, what happens? The first kind of round of things that happens is it gets changed to assembly code, typically, which is you have your machine language, which is usually localized to whatever kind of hardware you're using, and that is represented through assembly code to a human. So you interact with registers, which are basically hardware versions of variables. I think x86 has like 32 registers. That doesn't sound right.
I wouldn't say 32, but there's a decent amount.
It has a lot.
It has like 6 general purpose ones, and then it has specific ones for different flags.
Yes.
And for different, for like a carry
The flag register is like
Yeah.
itself a register, but then the bits inside of it are flags.
Yeah, so some registers exist for like where you are in the program and what function you've called into and what function you're going to return to when you end your call. Some registers exist to represent variables that you're currently interacting with at that stack frame. And then some variables can be even like specific to that hardware platform. Those are called model specific registers. You can have things like temperature control can be read in from those, and you can change fan speed. I think that one might actually be standard. So when you take in your C code, you pump it out to assembly. You can actually do this through GCC with the capital S flag, I believe, which will give you the assembly output of whatever your program is. So once that's done, it will go through the assembler? Yeah, the assembler process, which actually takes your assembly and it turns it into machine code. Usually it goes through 2 rounds of machine code. One is like object code.
It'll take it to object code,
Yeah.
and then you'll send it to a linker, and then the linker will link the object code into the final executable.
So you can use object code. That would be the equivalent of a library, or I guess you could have a DLL or a shared object. It's kind of weird at that point because you can sometimes execute those while also compile against them. DLLs being the example of that. Yeah, so your code compiles to your assembly and interpreter code. If you have like Java, you'll probably just go to bytecode and then immediately finish. However, some other versions of Java, like Android, can go all the way down to a language called Smalley, which is a just different kind of bytecode. Native code, so C++, C, and Rust. There's probably more, like Haskell, I think, can be compiled down. Those will continue to be compiled down right to your native executable. So that'll be a machine code binary, which, you know, it is a binary amount of binary data there. It's usually represented in hexadecimal, though. That will be tied to that hardware platform, and usually there's more dependencies that link it to your machine in some way. So it might be just be like linked to your OS. Usually it's not common that you're going to take something from Ubuntu and then immediately run it on Windows. Usually you do a lot of cross-compile. Yeah, in some scripting languages, compilation might not be done at all, because you'll just have a interpreter, like basically freeform compiling for you, / calling existing machine code. I think JavaScript, the older versions used to do that, but the V8 engine from Google now actually just in time compiles it down to machine code, which is pretty weird. Yeah, so dependencies, when you build a binary, if you're doing anything of like reasonable size, you'll usually do linking. Static linking is, you know, when you do hello world and you have include, I don't need to break out of that, and you have like include stdi.h, that is static linking. Wait, no, it's not. It's anything. Is it? No, it's not. Okay, that's static. So if you have a .lib or an object file, when you compile, it will take those objects and put them into your binary. So the pros of that are you have a more portable like program, but you have in just one single output program, but it can become much larger very quickly. Dynamic linking is kind of the opposite of that, where you have virtual references to whatever you're calling. So when you start at your executable, you'll have like a bunch of DLLs. You'll load those all into your executable's like program space and memory, and then it'll be able to interact with the objects through that. The pros are there. Obviously, it's a smaller binary size. However, you have multiple outputs or files to track. However, you can have a lot of programs sharing the same libraries. So like the C library is dynamically linked to pretty much everything on whatever your OS is. Runtime linking is a little bit different than both of those. So this is something you typically only see in malware or like maybe some video games. I think BattleEye actually does this through some weird like scanning method. So whereas these two are both like very standard and easily identifiable, this one you can actually obfuscate. So this will come up in malware analysis a lot, which is kind of out of the scope of this one. But if you call a file on disk by name, you can load it into your memory space of your program, and then you can basically treat that as another program space and then call the functions in it. That one's a lot harder to explain without seeing an example. But if anyone has the practical malware analysis book, that goes into a lot of depth on that. And then strings, typically you have user like readable strings in your binaries. Those literally get copied and pasted into a section. Data, I believe, not text. think it's in the data section for portable executables. Do you know what?
Yeah, it's in the data section. Text.
Yes, that's it.
Yeah, text is good. So you will be able to read those on a program. So an example is, let's go to, oh. So I have a hello world file here. You can see I have a user string, a user readable string called hello world. If I compile this, and then I run the executable, it'll say hello world. But I can run a program called strings, which is pretty standard for most operating systems that have some version of this, which will basically go through the binary and find any printable characters in any printable arrays of length 4 or more. You can kind of play with the options on it. It will print all that out. So that little, 20 byte program I had actually has several hundred bytes of just string data in it. That's from the compiler. But if we look in here, we can also see hello world. So that is physically just shoved into the program and then referenced later. So if we ever do anything with a password built into it, you should be able to see that. There are ways that when you compile things, you XOR encode them. That when you call them later, in your memory, it will decrypt them. So if you do strings, it won't show them, but you can still use them. That's comes up a lot in CTFs.
Java bytecode is the same way.
Yeah, Java bytecode is the same way. So we're actually going to do a problem. Does everyone have Ghidra set up yet? Is anyone waiting to set up Ghidra? How much longer do you have?
Well, I have it all installed, but I'm not sure how to link the OpenJDK to Ghidra.
What? Okay.
The Java.
Alright. Aaron's going to help you. Does anyone else need help? Alright. So the website for this is Battelle Cyber Challenge. Oh, I forgot. Yeah, Battelle/Cyber Challenge. So they have 3 challenges on here. One of them is called Feed the Magical Goat. That is a very, very simple reverse engineering problem. So just go ahead and download that. It's a Billygoat executable. It's in a zip file. So in this zip file, there's a single file called Billygoat. This will actually not run on Windows because it's a Linux binary, but we can let's make a directory for it. We can extract it and run it through Ghidra regardless of what system we're on, which is very nice. Is anyone still trying to figure things out for this? So if you have Ghidra set up, you can go ahead and open it. It takes a few seconds to start up. And apparently crashed the back monitor. Okay, it's there. Yeah, it is. So if this is your first time opening Ghidra, you want to go to File and then New Project. Ghidra is entirely project driven, whereas IDA, you can just grab a binary and throw it right in. IDA is another reverse engineering tool. I don't know if I actually have already goes. So actually, I happen to already have one called CTF that I've already imported this program into. So you create a new project, and then you right-click on your project. That's not right. You go to File, Import File, and then you want to select the Billygoat binary off your drive. This is kind of hard to see, but Ghidra doesn't really have a zoom feature, so sorry. Does I have this? Nope, that's Windows. Is anyone not here yet?
I think they want so we can
No,
Alright, so once you get the binary imported into your project, you just want to double click it, or you can select it and then click this little dragon here. Ghidra probably by far has the best animations of any NSA tool we've seen so far. So when you open it, a little dragon flashes up on your screen. I believe I already analyzed this, but I might be wrong. Oh, I actually did not open the binary. So if you open the analysis tool without the binary in it, you can just go to File, Open, select Billygoat. We can do this actually. I've already analyzed this, so I'm just going to retry this real quick. Delete. So I'm just going to do a fresh import so you can see exactly what I'm doing. So you import your program, it'll detect what format it is. It's not a raw binary, this is an ELF format because that's what Linux executables usually are. Hit OK. Here's a quick summary about the file itself. File name, the language ID, so this is a x86 binary, so if you don't have a 32-bit runtime on your Linux machine, even if you have a Linux machine, this won't run. That's apt install libc i386 if you want it. It was compiled with GCC, it's little Indian. That's just how the data is arranged in memory. There's other bits of information in here. There's apparently 56 functions, only 54 instructions. All right. So we can open Billygoat. Now say Billygoat has not been analyzed the first time you open it. You can just go ahead and hit yes to analyze it. The default options we've decided are pretty good. You don't really need anything in red because they're both prototypes and they kind of make things freak out. So, yeah, for like 99% of what you're going to do, just the default options. You should see a progress bar down in here for a couple seconds. However, Billygoat is a very small executable, so it's just going to like plow right through it and decompile everything. At which point you want to save with Control S so you don't have to re-decompile. If you put like a 30 meg executable through here and it takes like 3 hours to crunch, you want to save Ghidra immediately because if you close it, you'll have to like decompile the whole thing again, which will take another 3 hours, which I think I've done before. Did you do that?
Yeah.
Yeah.
I did that with one of the libraries from what's it called? From Terratime.
Yeah. Yeah. So also, if you need any help in Ghidra at any point, you just want to select a window. This thing on the left is the function graph, which I'll show you guys how to use in a second. But on the right, I think the default view has the decompiler. If you click the decompiler and hit F1, you get the help for it. This brings up the entire Ghidra manual, which is open to the page of the current window that you're selected when you hit F1. So this can be very helpful to get familiar with it quickly. It's not like super in-depth stuff on here because this Ghidra kind of does assume that you know a lot about embedded binaries, but yeah. Let's actually go back to the decompiler. So the decompiler basically just takes your code and turns it back into a C-like language, so you can represent it a little easier. So on the left side, we should have a symbol tree by default. You can go to the main function, which is you know, the entry point for pretty much every C program ever made, also C++. So if you just click on that, Ghidra will take you to it. You won't see this nice view, sadly. Oh no. Wait. Oh, that's all right. Yeah. It's the default window. So I've managed am just to close my left side window, which is the actual disassembly of the program. Does anyone know what that's called? It should be like right at the top.
Disassembly view, I think.
Oh, yeah, disassemble.
Oh, no.
That's not it.
It says listing colon.
What are the little
Billygoat.
buttons under, like next to the play button? You scroll through those.
This one?
That one.
Display bytes?
No.
That's pretty close. That's not what I want though.
It's just the listing Billygoat.
Listing colon.
Okay, thank you. Alright, cool. So this is kind of a more structured view of what the actual bytes are. Let me get to a function. So if you don't know assembly reverse engineering super well, this isn't going to be as helpful to you. So what you might want to do is open the graph view, which is the display function graph window. This will actually show you roughly the same information, while also show you the logic flow of the program. So these right here are all if statements. You can tell because they have a positive and negative flow. Once you get used to it, you can just kind of realize that's an if statement. Sometimes you can see while loops will have an arrow going back. There's no while loops in this program though, sadly. So if you also want to just jump to a function, you can hit G and go to main. That's the function we're going to work out the most of for this program. Sometimes you might find programs that don't have mains because they're like statically compiled with an entire C library. It's very rare you see that in a CTF, but sometimes someone puts in the effort. You might find a function called entry point at that point, because that's how the C library starts, but at that point, you might just want to do dynamic analysis until you actually get to your real main function. Okay. So let's start reading the code over here on the right. Let's try this one. So just starting from the top, we can see that this is a main function, and it has an undefined return type and one undefined parameter, and neither parameter is named. Because this is a C program, we can assume the param1 is actually called argc for argument count, and then arg2 is just argv. This is just standard for all C functions. There's also a third variable called environmental pointer, but we're not going to use that today. So you can also, if you right-click anything in Ghidra, there's a lot of context that you can change. So if we go to right before main, let's see, we can retype the return. So we can say, this returns an int because it's a main function, and that'll update for us. And I believe our argument count is also an integer. So let's just do that real quick. Oh, I renamed it. Cool. So as we read through here, we see a lot of variables are immediately declared. That's really an artifact of the C compilation process. You will see all your variables declared at top. That's because it forms the stack immediately. That's more like on the memory analysis side of things, but it basically declares all your variables in memory as soon as your function starts. So let's see. We have a local variable 18, which is a reference to our number of arguments. Kind of like args. P argc, sorry. It's a pointer to the argc. So we can also see that there's a variable that Ghidra automatically references as bin name here. So that's the first argument in argc or argv. So that's our binary's name. We can also see it sees a random function here with the current time. That's very common to see in C programs that call random numbers. So before we get in too deep here, let's go ahead and analyze strings. As I mentioned earlier, strings are built into your binary. In Ghidra, you just go up to Window, Define Strings. Yeah, Define Strings. What?
I just realized that local 24 is the bottom of the stack.
Where is that?
That plus 14.
Yeah?
I think that's just grabbing the location of the bottom of the stack.
Probably. Is that ever called?
Well,
I just know the number of bytes to get past like.
Oh, that's
EDI.
a stack canary. Yeah, you can see it right here. I think it's a stack canary. Maybe it's not. It has a stack check fail on that. So that's a little bit more advanced. That is a stack canary. There are ways in C to detect if someone has like overflown a buffer maliciously. Yeah.
I think it would make sense that it's a stack canary because if you override the stack, you're gonna run over that canary.
Yeah.
So it's probably just checking its value.
I think that's what it is. It's called a canary. We learn something new every time we do this problem. So my Ghidra install is also freaking out. If you see like my UI slowly break, I think it's something I've done to my machine. Hopefully you don't encounter the same issues. I had an issue last night where I would rename a variable and it would clone it and then not rename it. So it looked like I had just put something else on the stack for my function, which is a big no-no. Alright, so let's go back to our strings view. So window, define strings. There's a whole lot of strings in here, but there's also something called string representation. So if we wanted to go back in here and actually like change what appears for our view in Ghidra, we could just change that. So maybe there's something like worth finding in here. So you can see there's also a format string that's prefixed with flag and then encapsulated in brackets. So this is a CTF problem. So that's building what's called a CTF flag. If no one's ever done a CTF, usually you find a defined string that's a flag and it usually follows this format. So that's of interest to us. There's also, hey you found a hint. The Billygoat is single can, which is an @ symbol for a hint. So if we go back to the website, I did skip over this. There's a table of inputs we can give the Billygoat. We haven't figured out how to feed the goat yet, but we can find hints that way. We found a hint through strings. This is a hint about a hint. So if we can feed the goat, we can give it an @ symbol, which is a single can. Yeah. And then you should cover your webcam. That's not intimidating at all. Yeah. Good stuff. So we go back in here, we see there's a function called giveOffering that is statically called with a string chow down. If we double click on that function, we'll just jump right into it. Our param1 is a string chow down, so we'll just name it that. We can see there's an open call to that, so at some point we're going to read that. It's called a 0, which just means it's going to be read only. And it seems if our file doesn't exist, the Billygoat will look around and delete itself, which is what unlink does. So unlink binary name will just delete the Billygoat executable from our hard drive if we run this. So let's go ahead and actually try to do some primitive dynamic analysis. So I'm going to take a copy of that because we just saw that it does have the ability to delete itself. So if we run Billygoat 2 or copy, yeah. So have you ever seen a Billygoat with bow staff skills? Trick question, no one alive has. Yeah. So the Billygoat looks around, anger fills his eyes, and as we can see, the Billygoat has disappeared from our hard drive. So if we had a piece of malware we were inspecting, we might want to do it in a VM. We might want to keep a copy of it. If it deletes itself, we're going to have a hard time getting it back if we don't have a copy. So let's also try to use our previous hint about the file chowd was dot down. Yeah. So instead, if we feed it a single @ symbol through this file, which is through the giveOffering function, Jesus, please let me leave. All right. So let's copy Billygoat again to Billygoat 2. Oh no, really right. That's fine. Still copy. Okay. So our Billygoat gave us a hint. Goats have multiple stomachs. Magical Billygoats are no exception. The rumen processes organic matter. The reticulum processes inorganic matter. Without going too deep into that lines up with the types of inputs that we have for Billygoat. So let's zoom in further. So inorganic matches up with these letters. Magical matches up with these letters, and then there's types of matter, and then which stomach processes that. So if we go back to Hydra, we can go back to main, gmain. We can see there's 4 functions right in main that are all called as if statements sequentially. Fill, rumen, reticulum, amazum, abasum, opamazum. So it's very important here that you memorize the stomachs of the goat, because this is actually biologically correct. Okay. So if we go into one of these functions, we can see it's a series of if statements that is checking the inputs that we gave it, which actually matched up with the website. So the first time we solved this question, it was entirely in disassembly, which was not as nice looking as this. What, were you there when you did this?
Yeah. The graph looked very similar to that.
Yeah. So without what we see on the right, this is how the original problem looked when we solved it. This doesn't look like an if statement inherently, so it's a little bit harder. But Hydra just gives us this, which is the inputs in order, not their hexadecimal values. So this is way easier. So we have... Chat, can you take notes? So can someone remember that we have a comma, a semicolon, a period, and a U in that order? And then it looks like we have a parameter that we pass it that mutates our inputs and then returns them somehow. All right. Are you guys following? Does anyone have any questions so far? All right. Pass around this. Not going to look at the display graph correctly. So if we bent vim chow.down, we had a comma, semicolon, period U. Which one was that? Yeah. Then we go into reticulum. We have p at h underscore. Masm, we have a pipe symbol, PNW. Let's go back, please. Or opamazm, abamazm. We have BCR. BCR. And this up here is actually an obfuscated comparison. So we have hexadecimal 48, which is not a printable character. I think it is. Yeah. We're taking whatever our input is, and we're bitwise anding it with 7 capital F's and then a capital U. F's and then a U. Is that a U? Is it inside? Yeah. So, because we don't know what that is, we can just consult the table we had earlier. So, there's our capital B. So we have BCR and then a capital H in here. We can just assume that's an H because we're told what the inputs are. So if we feed these to the Billygoat, it should not disappear this time. We should get our answer. Right. Oh no, what did I do? And I forgot to copy chow down. Oof. Alright.
I have the order at least.
You have the order?
Yeah.
Can you read it back to me? Yeah.
Comma, colon,
What was it?
period, U.
Comma, semicolon, period U?
I thought you said colon.
A semicolon.
Oh, yeah.
Semicolon.
That was 8. Capital or lowercase?
Lowercase.
Alright, what are the other ones?
So it's uppercase P, at symbol, lowercase h, and then underscore. down slash
A pipe.
lowercase p, lowercase n, uppercase d.
Lowercase n.
N.
N. Let's go back. NW. All right. So this should be our input. I probably just messed something up. We'll just copy that. So what we've done here is we've gone through our program and we've followed the execution path to where we want it to go. And we've taken every single input we can give to our program and given it to our program in the correct order that it wants us to, via like this huge chain of if statements. Which there's 4 of these and each one has 4 if statements in it. What the hell is that? Alright, so the Billygoat is pleased with our offering, so we get the flag, which is living that goat life. So at the time of this CTF, this is really small, I'm sorry. At the time of the CTF, this was the answer that we turned in for points. That's really it. Does anyone have any questions about like the basics of reverse engineering? Cool.
Can we actually look into that stack canary?
The stack canary? Yeah. So some more advanced stuff for people who might not be super familiar with binary exploitation is if you have a user input and you don't check how much data you're reading in from the user input, say through the gets command. So man gets. The description for this function is never use this function, and we're going to explore why. When you use gets, it copy and pastes a string from the command line right into a buffer that you have in memory. The issue with that is your buffer might be way smaller than how much memory you have. So what it's going to do is it's going to just keep copying and then overflow the stack. So one of the defenses against that, like in the compiler side, is when you compile your software, you insert a bunch of functions and variables called stack canaries. So basically, every time you return from a function, you check a random value, or I think sometimes it's like
I think it's just the base of the stack.
Yeah.
Because that's where your return address is.
Yeah. Let's see what it does in this one. So we have that int canary on here. Yeah. So that becomes the, what is that? Int gs offset.
So I think.
So that looks like the bottom of the stack, like where it is, possibly. Not super familiar with how this function works. But converted to an integer pointer.
Plus 14 gets you from the base of the old base up to the bottom of the new stack. Because you do like old EDP and then like EDI, ESI, like all your registers, and then that plus 14 is the bottom of the stack.
So way down here, right before we return, we have if canary is not equal to, and then it checks for that same value it set it to. That means that we've overwritten the stack and like destroyed the canary, which is just a value that we check in memory. Are you shaking your head no?
No.
Okay, just moving. All right, and then if that is not equal to the original value, it goes through stack check fail, which I think is just a implied C function, and will just kill the program.
I never noticed that before.
It's stack smashing detected as the error you get. So I actually have a good thing we can check it with that. Let's see. So this is what this looks like on the, oh shit. So when we compile to not have a stack canary in it, we just give it no stack protector as a flag. So I have this binary that will kind of visualize through this horrible printf statement here what's actually happening when we overflow. So as you can see, we have a for loop here. It has an iteration count of 19, so it's going to go through 15 and then 4 more positions in memory in this array. However, our array is only 15 bytes, and we have an integer right past it called overflowed in that is intentionally meant to be overflowed into. So integer is 4 more bytes, so 15 plus 4, 19. So as we write A's in here, it prints out the memory. And we can see that our buffer fills up after 15, and then our integer actually starts filling up with the byte value for the letter A, byte by byte. So what that does is it drastically changes our original value from 0 all the way up to, is that a couple million? Like 10 million?
109.
Yeah, 109 million. Oh wait, no, more than that.
1 billion.
Yeah, so 1 billion. So if you have like a bank transaction that asks you for your password, and you go, my password is password, and then like a bunch of A's, and then somehow that value returns to how much money you have, you might, have an extra 10 or $1 trillion, $1 billion. So that's the basics of an overflow. We'll be inspecting that more next week as we go into like the very top level binary exploitation. So is anyone interested in learning how to do that? Because that's how like the OG hackers worked. The Morris worm, which was what, 92?
Around there.
Does anyone not know what the Morris worm was? So the Morris worm was like the first virus on the internet, and what it did was it just found other servers and like copied itself to them. The way it did that was through buffer overflows, because there was no protection or literature on at that time. And it actually did that 7 years before anyone documented what this was, like in a cohesive way. So you can copy code through here instead of like just the letter A, and then sometimes the program will execute that. So that leads you to the more advanced exploitation techniques, especially the binary level. So this is a lot different than anything web-based because you're actually copying the bytes of your program into another program. So ROP is an example of that, although ROP's really weird.
ROP's.
Let me reverse from ROP. So certain programs you can do this and you can get, this is arbitrary write, but you can also do arbitrary read, which is another thing entirely. So between the two, if you can do them arbitrarily to a program, you can make that program do really whatever you want at that point. This is all really abstract now, so that's the meeting.
Can you show them a visualization of the stack?
No. Yes.
Yeah, stack. Stack.
So your stack is just a sequential array in memory, basically. It starts the opposite of how most stacks are, or most arrays are, where you start at 0 and count up to infinity, however many positions you have. The actual like C++ stack frame, I can't zoom in on this site. There we go. The top starting value is infinity, and then as you add values to it, it counts down. That's not really infinity. It's very high value though. It's
What is it?
it's really high.
Yeah, it's a couple million.
Yeah, and then as you go into another function, you add another stack frame to it. You have the parameters to it, which are pushed on your original stack.
In reverse order.
In reverse order, yes. And then you have your return address for your original function. So this is kind of the more advanced side of this that we're going to like slowly lead into. You have your local variables are what you push onto the stack. So that's how we saw in Ghidra it had all those variable declarations immediately. The source code may not have looked like that, but the C compiler turns it into that. All right. Does anyone have any questions or inputs? No? All right. But you want to close the meeting?
Okay, awesome. So that was just like really basic overview of reverse engineering, how you do it, and what it is. We will go into the nitty-gritty stuff later on and actually start reverse engineering more difficult things. But I hope you all learned a little bit about reverse engineering. If you need other applications to, or if you want to use other applications, IDA Pro or IDA Free is downloadable and usable on different operating systems. It's great, but you have to learn assembly. So stick with Ghidra if you can. But that's going to be it for the meeting. Thanks for coming, everyone. Remember to fill out that election sheet if you want to run for a position. All of the positions are open. Go forth. Oh, Aaron has something.
Do we need to prepare slides for elections? Or like a vote for me slide or something?
Yes, if you plan on running for anything, please prepare some sort of slide or at least like something. Speech, I don't know, dance, anything. If someone gets elected off of a dance, I'm going to be
Have a
really
dance, it
happy.
has to be ballet, not be an interpretive dance.
Okay, but yeah, that's about it. At this point, I'm just rambling. Cool. Thanks for coming, everyone.